Hi, my name is Tomas Rosenstatter and I am a PhD student at the Chalmers University of Technology, and together with my colleagues from Chalmers and Gothenburg University in Sweden, we have been working on Remind, a framework for the resilient design of automotive systems. In order to get started, I will first talk about the aspects of automotive systems, the future architecture, as well as the definition of resilience that we are using, and then I will give you an overview in the work that we have done. So cars are quite distinct to other domains. So one of these aspects is, for instance, safety criticality. So in vehicles, a fault or an attack can cause or lead to immediate harm of the passengers or of individuals around the vehicle. So this is one aspect that is very important. And then we also have the real-time requirement. And other factors and aspects are low energy consumption, the costs, introducing new hardware or more resource requiring hardware would lead to immediate cost increase of a car. And we also have the lifetime, because vehicles usually live or stay around us for 15 years, which is around 150,000 to 300,000 kilometers. And during this time, quite many things can happen. It can change the owner, and we for sure also need maintenance. We need to replace parts, we need to update the firmware, and all of this is necessary or an aspect of automotive systems. And this might look quite similar to other areas such as trains or airplanes. But what we believe makes the automotive domain so distinct to other domains is that it's actually operated by millions of people every day around the world. So we have cars everywhere around us and we need to make them resilient. This is an overview or a concept of a new or the future architecture of vehicles. So now the move is towards a more centralized architecture, which consists of this core system. And this core system is usually 2 or 4 high-performance computing units. And these units are communicating with sensors and actuators that are placed all over the vehicle. This trend is seen for all vehicle manufacturers. So they all are going more towards a more centralized architecture. And how do we define resilience? So there's one definition from Laprie, which is basically saying the following, that resilience is the persistence when facing changes. So our definition that we have chosen to use is the following. Resilience is the property of a system with the ability to maintain its intended operation in a dependable and secure way, possibly with a degraded functionality in the presence of faults and attacks. So here, with this definition, we want to highlight that we are looking into faults and attacks that might occur during a vehicular lifetime. And the aim of this publication is that we want to lead designers to the informed and optimal selection of resilience techniques for the automotive domain or for an automotive system. And in order to do so, we have first systematically identified resilience techniques based on relevant publications, on existing work. And then we have come up with a taxonomy that comprises of 4 strategies of detection, mitigation, recovery, and endurance. And furthermore, we associate the identified resilience techniques to automotive assets such as hardware, software, network communication, and data storage. And last but not least, we have also provided guidelines that show how this framework can be used and also discusses trade-offs for specific techniques and solutions given a specific threat that we are looking at. So let's start with the overview of what we have done. So we have queried the Scopus database in order to find more relevant publications that are already looking into a collection of resilience techniques. So what we did is that we focused on surveys and literature reviews, and we included phrases or terms such as resilience, survivability, but also more dependability terms such as error recovery, fault tolerance, and so on. We have limited our scope of search to publications that have been published after 2010, and they must have been written in English. We've excluded hardware, FPGA, memory, and SDN, as well as wireless, because we want to look at resilience techniques that are more on a system level. We didn't intend to look at specific solutions or resilience solutions for software-defined networks, for instance. And what we then did was that we have looked at the most relevant publications, at the top 200 that have been returned by Scopus, and manually screened them and looked at their relevancy to us. And the outcome was 8 relevant publications and additional 3 publications, as well as 1 NIST document that we have already found before. And after having screened these publications and identified the relevant publications, we have worked on a taxonomy that is like in this layered approach where we have strategies on the bottom, patterns in the middle, and the specific solutions on top. And with this taxonomy, we also can help designers to immediately choose for each strategy which techniques they want to use. And we additionally also provide these guidelines that are based on specific threats. And here we identified certain techniques that can mitigate this security threat, and we discuss the trade-offs when using these, such as energy consumption and so on. And here you can see the domains and disciplines of the identified publications. So we can see that fault tolerance and resilience is quite prominent, but we also found some security publications, as well as one publication that is a survey paper on dependability. So it also covers fault tolerance, but not only, it covers fault prevention and so on as well. So if we look at the taxonomy again, we can already say that we have the strategies on the bottom, which define the overall goal. And then we have the strategy of detection. We need to have strategies or techniques that are detecting faults and attacks. We have mitigation techniques, techniques that are keeping the system operational, and recovery techniques that are bringing back the system to an operational state. And the fourth strategy is endurance, which has the focus on lasting resilience. So it's not about taking immediate actions, it's more looking in the long term of providing a resilient architecture. And in the mid layer, we have patterns. So there are more specific, more detailed descriptions of how a strategy can be implemented or realized. And then we also have these techniques and solutions that are actually already specific methods on how to realize a specific solution for the automotive domain. And here we can see the strategies. So we can see detection, mitigation, recovery, and endurance. And what we can also see is that mitigation is intertwined with detection and recovery. So here we have, for instance, redundancy as well as reconfiguration, which are providing both. Like redundancy provides detection as well as mitigation, and reconfiguration can be used for mitigation as well as recovery. So now I'll give a brief overview of the patterns that we have identified. So we have identified specification-based techniques that are like signature-based detection or runtime verification. but we've also found anomaly-based detection, prediction of faults and attacks, as well as redundancy. And redundancy is also containing diversity techniques, because a pure redundant system suffers from the same design flaws, so we need to have mechanisms that introduce some diversity into the system. For instance, N-version design, recovery blocks, N-variant systems, and so on. And for specific mitigation techniques, we've identified adaptive response, runtime enforcement, as well as reconfiguration and reparameterization. Pure recovery-based techniques are migration, checkpointing and rollback, and also roll-forward actions. And for endurance, we've identified as a big part all these self-strategies, like self-adaptation, self-awareness, and self-organization. But we've also seen techniques or patterns for verification and validation, for robustness, as well as forensics, in order to have the evidence that we need in case that a fault or an attack has happened. So if we look back into these techniques and where these techniques come from. So in this illustration, we can see some of the selected patterns. And here we can see the disciplines that the papers originate from. And we can see that quite many of these techniques are already from resilience, from other domains, but we can also see that the identified techniques are also in the area of fault tolerance as well as security. For the other way around, where or from which domains do these techniques come from? So we can see here that it's more equally distributed. So we have cyber-physical systems, we have high-performance computing, as well as cloud computing, but also the other domains such as vehicle controller design, software engineering, and so on. So what we can see here as well is that we've identified quite many cloud computing and high-performance computing techniques for the automotive domain. And this is due to the fact that we actually already consider this future architecture where we have a hypervisor-based virtualization on these centralized nodes that are in the vehicle. And here we can see overall our techniques, the remind resilience techniques, how it looks in the publication. And additionally in the publication, we also point to the specific techniques that have been already designed or developed for the automotive domain. So if you want to go into more detail on this, please have a look at our paper. And now it's time to say thanks for watching my video, and I'm happy to answer any question during the Q&A in a short while. Thank you very much.